Welcome everybody to today's webinar, where we'll be doing something a little bit different, and I hope you'll enjoy it. Today we'll be going through a model created by one of our clients, ADD Consulting of Lurgan, for the structural design of a commercial 3-storey building in Cookstown, based in Northern Ireland. We put the word out to a few local consultancies at short notice here. We were looking for a project that had common design issues that structural engineers could relate to or faced regularly. A model that was designed exclusively in MasterSeries, and one that would allow us to show off the modules and features of the software. So the Cookstown Credit Union project fits the bill perfectly, as you'll see today, as it is a multi-material building with a few challenges, and our aim for the webinar is to provide new users a feel for what is capable within the software, plus provide existing users with some practical tips and maybe some ideas or suggestions on how to deal with different design situations. But of course, none of us is to be taking this design advice. So today I'll be using SketchUp again, purely as a presentation tool, as it will allow us to display the context of the building within the surrounding site and showing some detailed interfaces, and it'll allow for some layering and construction sequencing as well. We were able to use a fabricator's drawings, which were derived from the initial MasterFrame model, with the help of our MasterCAD BIM Integration module, which we can touch on later. After I go through some of the design features, Andras will be able to touch on some of the features I will talk about within the software itself. As always, we will be taking questions in the chat box, and we would love to hear your feedback and comments on your own experiences, or maybe design procedures for the topics that we will cover. To give you a bit of context for the site, I'm going to bring over a short video that ADD produced on the site. So it's showing the structure nearly complete. As you can see, the site is in a town centre. There are a couple of properties at the end of this row of houses that were required to be demolished before the construction began. So I can show you these in the 3D model. So thanks to ADD for that. So starting at the substructure and looking at the foundations, the local site investigation showed the ground to be soft clay with a high water table present, reducing the allowable bearing capacity of the soil. So SPT values were ranging from 5 to 8 or so within the first 3 meters. Groundwater was encountered about a metre and a half below ground level. So shallow foundations were opted against, and as you can see, the proximity of the neighbouring property meant that excavation depths for the installation of the new foundation were to be limited to avoid undermining any existing foundations. Piles were chosen, so steel-driven milling piles with a safe working load of 275 kilonewtons were specified. They were around 225 mil diameter, and these were designed as friction piles and not end-bearing. So they were designed as spring supports in MasterFrame, taking into account the allowable settlement of around 10 millimeters. So Andras will show you how that can be applied in MasterFrame later. Around the neighbouring properties, pre-coring was required to minimise vibration, and these are donated by the red piles that we can see. And the contractor adopted a hit and miss sequencing for the temporary works for the installation of the ground beams closest to the neighbouring property to safeguard and avoid undermining its existing foundation. So without actual details on that, we don't have actual details on the existing foundation footprint or levels. I've just come up with a slide here on how I believe that a typical sequence would have looked like for this hit and miss. So the ground level would have been locally remained higher adjacent to the existing foundations, with the piles also driven at a higher level, then locally excavated for the installation of each ground beam and then the piles cut back and the ground beams cast. Again, I'm not too sure of the details of this, as ADD weren't directly involved in the temporary works, but consideration of the adjacent property was critical to the permanent works design as well, so I thought it would be worth mentioning. And the ground beams, they were modelled in MasterFrame, so we have the ability to incorporate pile cap design within MasterSeries itself using the pile cap design module, but here the ground beams are directly supported by the piles and they run continuous over the top. So the ground beams shown here are mostly 900mm by 600 deep grade D35 concrete, and they are detailed to include 75mm cover below to allow the piles to sit within and run continuous. So the ground beam closest to the neighbouring property, running parallel, as you can see there, that's set higher and is supported by the lower ground beams that were installed during that hit and miss sequence. The ground beams are designed to take loads from the riser wall, which supports a two-way spanning in situ ground floor slab, and the masonry wall panels around the perimeter of the building manually applied as line loads in MasterFrame. And then it also takes the odd column load where columns are sat offset from the pile locations, i.e. not directly below. The ground slab can be modelled again in MasterFrame, and the ground floor slab in this building is a suspended in situ slab cast on top of blockwork riser walls, as we can see. And for the purposes of this presentation, we have included it in the MasterSeries. I'll show you an example of that in the MasterSeries model, but in reality, ADD modelled the FE surface separately from the main model for a few reasons. The blockwork riser wall means that we're introduced with a modelling challenge, and that we now have to think about the behaviour of the block wall and its interaction with both the ground beams and the FE surface. So this is an important point to highlight, as it sometimes is a common modelling mistake made by designers using FE packages in general. I can actually pull up a cross report specifically referring to incorrectly modelling blockwork walls as FE surfaces within an FE model. A common mistake is to model the blockwork wall as an FE surface in an attempt for the model to simulate vertical support to the ground floor slab to transfer the loads to the ground beam below. So the green arrow, as we can see, but if we look at the red arrows, we don't want to assume that there's any capacity for the block and mortar wall to behave like a deep beam or act compositely with the slab and ground beams by being able to contribute to providing any bending resistance, nor can we assume that the wall can resist horizontal shear stresses longitudinally, nor transfer these stresses between the slab and the ground beam. So hopefully with a bit of background and understanding of beam behaviour and the different associated stresses, you should be able to understand the issues with this approach. And so referring back to the report, it is suggested to alternatively model the supporting walls as a series of pin-ended columns within the model at close centres to simulate the vertical load transfer. Practically speaking, considering that this approach eats into the number of members available in your frame, which could be an issue if you have a member limited version of MasterFrame, for example, and then introducing a large number of elements like this can also make the model a bit more difficult to manage. What you could do as a simple alternative is to apply the loads from the slab as a two-way spanning area loading panel within MasterFrame and accounting for its stiffness as well. And then you're able to design the ground beams non-compositely. And then whenever you're doing the design of the FE surface, you can just copy that across and with all the geometrical properties and do the design of that separately. As I mentioned, for the purposes of today's webinar, you can simplify the frame and you can show it as such. As well as slabs, we can model concrete walls within MasterFrame as finite element surfaces, and we can also now design reinforced concrete walls within the upgraded Concrete Slab and Wall Designer, which is our finite element add-on module. The inclusion of the wall design is only a recent upgrade last summer, and in fact this release came after the design was initially carried out by ADD so it wasn't used as part of their initial module. But we do have recent webinars where we go into detail on the reinforced concrete slab model designer, so you can check those out for a bit more detail on that. So we can talk a bit about the steel frame and the selection of steel as the material of choice here. From a structural perspective, the main frame could have been designed as a steel, concrete, or even a timber frame, as the spans were fairly modest, around 6 or 7 meters maximum spacing between columns. But for this site, the foundations were critical, and keeping the loads on the foundation line was a priority, so concrete was less favoured. And structurally, timber could have been chosen for the frame, but there were some specifications within the client brief which ruled out timber as a suitable construction type fairly early on. So steel was chosen for the frame. It is a common construction type in Ireland, so there are plenty of locally skilled contractors and fabricators facilitate this type of construction, and the site wasn't in a really restricted location, so deliveries for longer members wasn't a limitation. The lateral stability system was kept in steel as well, as there was no added advantage for specifying concrete shear walls, although that can be also designed within the concrete slab and wall designer. And I should also mention maybe wind loads were applied with a MasterFrame as well, using the wind analysis module. Precast concrete floor slabs were specified for the floors, and timber joists for the roof and canopies. And I'll talk a little bit about the development of the model and the workflow adopted here from concept to final stage. And I realised I don't have the timber joists shown on there, so I'll turn those on for completeness. So yes, so talking about the development of the model and the workflow adopted from concept stage to final drawings, and as it's fairly typical of the type of workflow that I personally would have adopted in the past, and I know it's fairly common still. So the green steel frame model we're looking at started off life as a MasterFrame model. The conceptual structural arrangement was sketched up in paper following the architects sending through the architect's plans, and then the steel frame was then built up in MasterFrame, where the analysis and design were carried out. This building was fairly straightforward, but for more complex arrangements, a popular option is to import a CAD drawing as an overlay in the MasterFrame to use for a maximum accuracy. So in MasterFrame, the model was then linked to Revit using the MasterCAD BIM Integration module, which allowed for the development of the final CAD drawings. We're always interested to hear how people use the MasterCAD BIM Integration. So if you've any experiences you think are worth sharing, just let us know in the chat box. And if we go into more detail on the steel frame, so the frame uses a mixture of UBs, UCs, hollow sections, angles, channels, and flats. And we can model steel beams with web openings, and in this case, circular web openings in MasterFrame as well, with regular centers. We can also design compound sections with top or bottom plates, and in this case, bottom plates to support the precast concrete slabs. We can assume diaphragm action on this floor to be able to model a stiff deck in MasterFrame, but it requires a minimum of a structural grout between the joints. We can also model eccentric loads on members in MasterFrame, in this case for beams that are carrying loads from masonry walls. And for this detail, the fabricator has used plates at close centres welded between the flanges of the beam to take the masonry support brackets. Our steel connection design module as well. So in this building, the fabricator carried out the design of the steel connections, but ADD used MasterSeries Steel Connections Designer for the preliminary design to ensure compatibility with their frame design for the different connections arrangements, such as the four-way beam to column flexible end plate simple connection you're looking at the minute. We've got a beam to beam flexible end plate simple connection, plus we can also specify flange toe plates here if required as part of the latest version of MasterSeries. An X-brace connection with steel flat plates onto the column in this case, or you could do it onto the beam or both. We've got an example of the base plates, including the brace connection. An example of a moment connection here we've got a fairly basic cantilevered canopy. We can also specify beam over column and column over beam connections, which now includes hollow sections in the latest version of MasterSeries. In our previous webinar, we go through all the different types of connections in the software in a similar format as I'm just showing here now, but it includes over 20 different types of connections in total that can be carried out. So these are just some quick examples of connections in this frame, but it's nice to pull up the different connections in a real world application. And the precast floor slabs, as they are a third-party proprietary product, they're not designed in the software, but they can be applied as gravity panel loads within MasterFrame, along with the associated dead and live loads. And as mentioned previously, the precast slabs here provide diaphragm action for the floor and can be modelled in MasterFrame as a stiff deck with sufficient detailing by the designer using the relevant structural grout or topping details. With the option of modelling and designing timber joists within MasterFrame, personally I would recommend against modelling all these individual joists throughout. As we can see here, I've actually got a plywood deck sort of covering that as well. Maybe I'll take that off for a second. As I say, I would recommend against that, as again, you're increasing the number of members in the model, which isn't ideal if you're on a MasterFrame version with a member limit. Plus, in my experience, too many members like this can be troublesome if you're making amendments to the geometry of the frame. For example, if you have to move beams or columns or shift nodes around, or if you're deleting members, it could affect your loading panels, your stiff deck panels. So in this case, actually, the roof acts as a diaphragm with the timber joists forming part of a stress skin panel, which are glued and screwed to the timber, the plywood timber sheets. And similar to how the precast floors and Insitu floor slabs were modelled, in MasterFrame we can apply the dead and live loads as a gravity panel load, and then assign stiff deck properties within MasterFrame to define the diaphragm action for the floor. And then we can separately design the timber joists within the standalone timber module within the software as well, or else if we did do an individual panel, if we want to take a worst case individual panel, we could do it within MasterSeries or MasterFrame integrated as well. Finally, we can look at we can make good use of the MasterSeries masonry wall design module here as well. We have a cavity block wall that wraps around most of the structure. The most critical design example for this project was the panel we're looking at here now with two openings. So if we look outside the building, that's where it is. I've kept the cavity wall off until now, so we can see the structure. Andras can show you just quickly how the panel works in the masonry wall design module. We have the advantage within the masonry wall design module to use the yield line analysis, which is exclusive to MasterSeries, over the traditional Eurocode or British Standard subpanel methods. And I think maybe Andras mentioned earlier that you need the advanced yield line analysis for this particular panel to work. So just to finish, I can do a quick run through for each of the floors, and then we could talk a little bit about the MasterSeriesLCA option as well. So I'll just open up a web browser here. So all the structural elements within the model can be populated automatically by using MasterSeriesLCA, which is integrated with MasterFrame. So carbon calculations can be created as part of an LCA, which is short for a life cycle assessment. We've written some blog posts on the topic last year covering both regulatory and financial benefits to be able to produce life cycle assessments alongside your structural model. And I'll just summarize them here now. And from a regulatory perspective, Part Z, it's an industry proposed amendment to UK Building Regulations 2010, and it is aimed at introducing legislation toward mandatory reporting of carbon emissions in the built environment, along with limiting embodied carbon on projects. And then there's also financial benefits to carrying out life cycle assessments with your designs. For example, you will be able to get the opportunity to contribute to green buildings which are buildings issued with certification from the likes of BREEAM and are now standard as part of many government and local authority frameworks. And here, there's several reports that show that these have even proven to be a good investment for private investors. So these are things to consider from a financial perspective. So considering both upcoming regulatory amendments and financial benefits, we believe it makes sense to start looking at producing carbon calculations for your structural designs. And if you're already using MasterSeries, MasterSeriesLCA is a simple, cost-effective tool to integrate and be able to have the ability to integrate with your MasterFrame and start producing reports for your designs. New users have the opportunity to have an extended trial as well to test it out on maybe your current model and get used to producing reports, which can ultimately benefit your business. So thanks for taking the time to listen. We're always looking for case studies to use in the future, so do get in touch if you would like to see your projects showcased, whether it's on a webinar on the website. It's nice to see how the software is being used out there. So we'll maybe share a form when the video gets posted up, where you can fill out an application to get your project used as a case study. So thanks for your time. I'm going to switch you back to Andras now and go through the MasterSeries software with you.
Okay, thank you, Patrick. Okay, so this is the 3D MasterFrame model. As Patrick already presented, that this project is a multi-story steel-framed structure supported by steel pies and concrete ground beams. So let's see how the engineers modeled the structure in the MasterFrame. So the beams and the columns are mainly S355 standard UB and UC hot rod cross sections. However, they used cubes and hollow sections where the architectural concept required. We also have a bigger UB with several circular web openings on the second floor. The ground beams are simple rectangular concrete members. We have vertical X braces in both directions as well, here around the staircase and around the opposite corner. This bracing system provides lateral stability for the building. The bracing members are tension-only steel flat bars. Timber joist beams on the roof were not part of the original model. They were designed separately. However, I added some of them to present that it is possible to analyze and design them inside the MasterFrame. The building is a simple construction, meaning all the beams are simply supported, except the cantilevers, which support the canopies. The canopy here and here on the roof, and of course the connecting beams are also continuous to avoid torsion in the supporting beam. As Patrick already mentioned, that the ground beams are supported by steel pies. The support effect of the pies has been mimicked with two types of point support. In the horizontal X and Z directions, the engineer used static support at each positions where there are pies. These static supports prevent any horizontal movement. In the vertical direction, spring support with 27,500 kN per meter spring stiffness were used. These supports allow some movement in the vertical direction. So this is our vertical support, swing support. Horizontal supports are normal static supports. Let's move on. On the first and the second floor, we have recessed Hollowcore slabs. These slabs, through diaphragm action, distribute lateral loads back to the bracing system. The slabs themselves haven't been modeled. To model the diaphragm action, semi-rigid stiff decks were added to the levels. The semi-rigid stiff deck is based on an underlying finite element surface, which models the slab based on the slab thickness and its Young modulus. In this example, the thickness of the Hollowcore unit was used for the thickness of the stiff deck, which is 200 mm. For the Young modulus, value, the usual 25 kN per square millimeter concrete value is applied both level. Okay, let's review the loading. The area dead and live load were applied to the model using floor and roof area loading panels. Area loading panels is an extremely useful tool in applying gravity dead and live load across the floor and roof areas of a model. It enables you to apply loading to floor panels and have the loads automatically distributed onto the members around the perimeter of the panel, depending on which direction you have chosen to span the panel. The panels on the first and the second floor and on the roof are one-way spanning. The spanning direction of the panels follow the spanning direction of the Hollowcore slabs. However, on the ground floor, there is an Insitu concrete suspended slab. Thus, here, the area loading panels are two-way spanning. The load values of each level were not defined here, panel by panel, but as a level default, loading for each level on this levels and loading construction default screen. The default loadings that are entered on this screen, this level and loadings construction default screen, are automatically applied to all the area loading panels in the levels. There is only one area where the level default level default loading was overridden, and that was the canopy here on the first floor. Significantly smaller dead and live load were applied to the canopy than we have on the first floor slab. So here we have the current dead and live load loading live load. Let's turn on the gravity, the visualization of the gravity area loading. So on the first and the second floor, we have the same 8.55 kN per square meter dead load and 2.5 kN square meter live load. On the roof and on the canopy, we have again the same dead and live loads, which are 0.6 kN per square meter and dead and 0.75 kN per square meter live load. And on the ground floor, we have a very high dead load of 10.9 kN per square meter and the live load of 5 kN per square meter. The surface of the perimeter walls were added as a normal UDL to the members for those beams where the masonry wall sits on the outer side of the beams. An additional torque eccentricity was applied. Torque eccentricity has the effect of offsetting the member loads from the shear center of the member and creating a torque load on the member. So this is how they model the surface of the cladding. The wind loads in all the four directions were generated and applied using the MasterSeries wind analysis module. The wind cases, of course, not only contain the global wind loads, but combine the wind loads with internal pressure and sanctions as well. We can see the coefficients, wind pressures, and zonings applied to the panels in all the directions. The wind module defines the wind pressure values based on the site location, which is in this project is Cookstown, Northern Ireland. And yeah, here you can see the calculated dynamic pressures and bed speed and the applied in pressure for the master frame. Yeah, wind panels. So similar to the area loading, the wind loads are applied to panels, wind panels. The panels are horizontally, the wall panels are horizontally spanning, while the roof panels span in the shorter direction. Bracing elements have a special bracing property on them, from which the program knows that even if they lie in the plane of a wind panel, these elements do not carry any loading from the wind load. While we generate the panels, the program automatically identifies the type of the panel, so we don't need to tell the program that this is a roof panel or a wall panel. The program already knows that this is a roof panel and this is a wall panel. And if we have a panel where we have wind load on both sides of the panel, such as a parapet or a canopy, like here, the program intelligently identifies these panels and applies the wind on both sides setting on them. Some points the engineers needed to apply a small trick to form the panels. To form the panels, there must be members on all sides. However, for example, in this corner, we don't have a column, or here. Or here at the balcony, there is no horizontal member on this side of the panel. Thus, members do not form a closed shape and the panels cannot be formed. To overcome this issue, the engineers used dummy members. These are the light gray lines. The dummy members just help with modeling. These are not part of the analysis model. Okay, we can also take a look at our different load combinations that were generated. If we go into our load cases, we will see that we have that plus live load cases, that plus live plus wind, and that plus wind load cases, both ultimate and service cases. The load cases have been generated according to the Eurocode using our auto function. With this dialog, we can generate all the automatically possible load combinations based on the selected type, service, and the ultimate types. If we go into our load combination tab, we will see here all the different load cases with their combination factors. Okay, before we go into the design, let's have a quick look at the analysis result. We have 75 load cases. Okay, so it's ready. So let's quickly check the deflection first to see how our model works. In that plus live ultimate load case, the top of the model moves down with a maximum of 25-30 mils and deflect with 3-6 mils in the x direction. And we can also see that because of the vertical spring supports, the whole model moves down with a 10-13 mil. But of course, we can see the result in other load cases as well, or we can see the maximum and the minimum values by selecting one of the envelope result. But we can not only look at the deflections, but also the member internal forces. Maybe we want to take a look at our bending moment or shear force, for example, in grid B. We can always increase this diagram to make it a little bit more visible. So this is our the bending moment, and this is our shear force in the load case one. Okay, all work as expected. So let's move on to the steel design. Okay, all the structural elements were designed to the Eurocode 3. For the beams and the columns, the engineers applied the general axial with moment check, which includes both local capacity and buckling checks. To the bracing element, the strut and tie check was applied. Looking at the beams, we can see that all the beams are unrestrained, so no lateral restraints, and the used buckling length is 1L. For the deflection limit, the engineers used multiple criteria. In the live only service cases, the limit is the maximum of L over 360 or 25 mil. In the DET plus live service cases, this L over 250 or maximum 40 mil. On the second level, there is a special beam with a couple of circular openings in its web. Looking at the design of this beam, the MasterSeries extended the general part of the check and applied web opening checks at the dominant position, and this calculation based on this SCI P355 publication. Looking at the columns, we can see that the connecting beams are used as lateral restraints for the design, and the buckling length is 1L for each portions. So if you run a scan for failures, we will see hopefully that all members pass the design criteria. Yes, all good. So all the steel member passes the design criteria. No failures. Looking at the critical unity ratio, that we can see that the most utilized structural elements is this short column, and this beam near the staircase on the first level. Okay, so let's move on to the concrete design. I'm gonna close the steel design and move forward to the concrete beam designer. So the concrete ground beams were also designed in the MasterFrame. The depth of the ground beams is the same, 600 mil at each positions. However, their width varies depending on the loading. So we have 600 mil, 750 mil, and 900 mil wide ground beams as well. The applied reinforcement is simple. 20 mil bars at both sides. So this is the used longitudinal reinforcement for all the ground beams. 20 mil bars both sides, and we have 4 legs of 10 mil legs at 200 mil, and it works. Just a few words about the timber design. The timber design function is pretty simple and straightforward. The MasterFrame automatically applies the axial with moment design check to each element and carries out the design checks accordingly. We can run a scan for failure to check if there is any failing member. However, they used 50 by 216 joist works at each position. And the last thing I plan to show you in the MasterFrame is the steel connection design. As Patrick already mentioned, the steel connections were designed by the steel manufacturer. Our customer only did some checks over the designed connections. The design of the connections can be carried out inside the MasterFrame. In this case, the program automatically picks up the geometry and imports all the loadings from the frame result. We can design moment connections. We can design simple beam to column connections, or beam to beam, simple beam to beam connection. For example, this is one of our latest connection types, where the beams connect to toe plate with flexible end plate. We can also design base plate connections and bracing connections as well. This is the basic connections to base plate, and this is another bracing connection types to a column web. And as Patrick already mentioned, after the design was ready, the structure was exported to Revit using our Revit bidirectional link for the detailing. This is the IFC model, the steel structure with all the connection details. So that was the 3D model. Before I finish the webinar, I will like to quickly bring up another module which was used in this project, and this is the Masonry Design module. So this is one of the this is the dominant wall panel. So this is a 6 meter long 6 meter long masonry wall. The height is 3.6. This is a cavity. This is a cavity masonry wall. The edge fixity is fixed on the bottom and pinned on the left and right and on the top. The masonry units are concrete blocks, both inner leaf and the outer leaf. The strength is 10.4. We have 2 openings. The loading is very simple. So the wall carries only just loadings, just sulfate from a level above, and we have out of plane loading, a wind load 0.7 kilonewton per square meter. The design is ready. So I've used the advanced sheet analysis to calculate this masonry wall. As you can see, it's okay, so it works. However, this is the advanced sheet analysis, the method of the inside in the MasterSeries masonry module. But as you know, you can use not only the advanced sheet analysis, but you can try out how the design looks like using the old-fashioned sub-panel methods as well. So if you turn on the line analysis, then you can see that this panel, the wall panel, actually fails, and this is because we have slender sub panel. So this is the left panel is the dominant wall panel. And yeah, this fails. We can try the other direction as well. So we can split up the wall horizontally. So if you want, however, this case is even worse, and this is because we have this very long, slender top panel. That's all about the project and the softwares were used in this project. So, ladies and gentlemen, I would like to thank everyone to attending today. I hope you enjoyed and learned in this presentation, and see you on our next webinar. If you have any questions, you can get in touch with us on our usual channels. If you want to try out the software, just go to the MasterSeries website and fill in a request to do so.